Alright, now we're looking at this problem. The half-life of a certain element is about 5,700 years. Use the radiometric dating formula to complete parts A and B below. A piece of cloth is painted with organic dyes. By analyzing the dye in the cloth, it is found that only 61% of the certain element in the dye remains. When was the cloth painted? A well-preserved piece of wood found in an archaeological site has 12.4% of the certain element that it must have had when it was alive. Estimate when the wood was cut. So this question involves our half-life formula. So let me write my half-life formula on here. It looks like this. The value, it doesn't tell you the value of Q or Q sub O in this problem, but it does tell you that ratio of Q, the new amount, to QO, and that ratio is 61%. Now, I can take this formula, the half-life formula, and if I divide both sides by Q sub 0, the right side, the Q sub 0s will divide out, and I will be left with Q over Q sub O is equal to 1/2 raised to the T over T half. And in this case, this ratio is 61%, or written as decimal 0.61. And then our T half, the half-life is 5,700. So I'm going to take, and in order to solve this, what I have to do is use logarithms. But in Math 119, we don't use logarithms. We don't learn about logarithms. But if you had it in the past, you're welcome to use it. The way you would do that is you take the log, what's called the log of both sides. So and when I take the log of both sides, there's a logarithm property that says I can pull down the exponent in front. So rewriting everything else, and now the exponent can go out in front of this. So now I would have log of 0.61 is equal to T divided by 5,700 times the log of 1/2. Well, I'm trying to isolate T, so let me divide this side by 1/2, log of 1/2, and this side. So that will cancel, and I'll be left with log 1/2 on the bottom is equal to this. And now to isolate T, this is T divided by 5,700. So I'd multiply both sides by 5,700. This will divide out here. And then my answer will be this. And so I put that in my calculator. And there's a log button found on the calculator to the left of 7. So I would put in 5,700 times the log of 0.61 then I have to remember to close the parenthesis there, because it's taking the log of just 0.61 divided by the log of 1/2. And then again, close that parenthesis. I enter, and I get 4,064.77. So this is my answer. Let me write it here. For the years. So let me go back to my question and see how it wants me to input it. This is round to the nearest 100. It doesn't say hundredth, but 100. So where's the 100th place? That is here. Look 1 over, and that's a 6. So it would be 4,100 years is t. So that's how to do this using logarithms. But we didn't study logarithms here. So instead, I'm going to go back to my original equation. This was 1/2 raised to the t over 5,700. And just like I did in the prior problem, I'm going to take and I'm going to estimate. So I want to see what values for t I can put in here to get this right side to equal 0.61. So let's try some values. So I'm going to say t, and we're going to call the right side q over q sub 0. So now I know the answer is 4,100 years, but if I didn't, maybe let me try some things. Let's try 5,000 years, because I'm using large numbers since this bottom was large. Let's try 4,000 years, and let's see what we get. So bringing the calculator back over. So 1/2 raised, oops, I need to put the parenthesis in there, raised to the 5,000 divided by 5,700. So that's 0.54. So that was too many years passed. So I hit second entry, and now I'm going to change this to 4. Okay, so that's 61. So that's a little high. So if I change this between 5,000 and 4,000, let's try the 40. So that's where I get the 4,100. And I can leave it at 4,100. If I go to 42, because it says around to the 100th place, so I don't have to get too precise. If I go to 42, that could work also. Well, no, I can't, because I want 6,100. So this one is a little too low. So it's going to be in the 4,100 range. And so I put 4,100 in here because it's an approximate nearest hundreds place. Alright, so I'm finished with part A. So now I'm looking at part B, and it says, well, I'm talking about now the piece of wood. Still the same half-life of the element was the 5,700. So this time I'm using this formula, the same formula, but now this q over q sub 0 is the 12.4%. And so let's put that in. And we'll put our half-life in. And again, we could use the logarithms, but our class does not cover logarithms. So instead, I'm going to use an estimation. And so I'm going to try some values out. I'm going to put some values in for t. and see what I get for this Q over Q sub 0. So again, dealing with very large numbers, and this time I want to go to a very small percentage. So let's try 6,000. And let's try 8,000, and let's see what we get. So pulling over my calculator. 1/2 raised to the 6,000 divided by 5,700. I get 0.48, so I'm not low enough yet. So let's see when I do the 8,000. Not low enough yet, so I'm only going up 2,000. I've only gone down about 10%. I'm just going to copy these over. This was 48%. This was 38%. So let's pick some larger numbers. Maybe we'll go up to 12,000. So I'm going to hit second, enter, and I'm going to change this to 12. Now I need to insert another 0, so second, insert, 0. So now I'm at 23,000. So I'm getting closer, but still not quite there. So let me jump quite a bit here. Let's jump up to 16,000. And this one says round to the nearest thousand. So I would have my answer 6,000, 8,000, 12,000. So if I change it to 16,000, I'm getting closer, a lot closer. So let me go to 17,000. All right, there I've got 12,000, 12%, I'm sorry, 12%, 12.7%. I can't get any closer because I'm rounding to the thousand, so it has to be between these two. If I go another 18,000, this number is going to be smaller and would not fit. So my answer I would choose 17,000. So we saw that 16,000 gave us 14%, and the 17,000 gave us 12.7%. So somewhere in between here, but because it says round to the thousand place, not thousand place, this is going to be my answer because it's very close to 17. All right, so that's how you do those two problems.